So this is problem 41 of chapter 20 of Giancoli 6th edition. So what I have here is the one wire carrying this current of 2.5 amps and another rectangle is a rectangular wire carrying the same amount, the same current. Okay, and what we want to know is the magnitude and the direction of the net force on this loop, on this rectangle. Okay, all right, so let me focus first on the current, on the force between this current here on the top and the current on the top part of the loop, this one in green. Okay, so they are moving in the same direction, so we know that there will be an attractive force, so we know that there is a force here pointing up which is attractive. Okay, now how about the force on this other side here where the current is going down? Okay, well, let's think. The magnetic field caused by the current that I'm calling I1 on that wire that is by itself, with respect to this, all this region where the rectangle is, creates magnetic field going into the page. Now, everywhere here we have magnetic fields caused by that current on that isolated wire going into the page. Okay, and this is why this green force here was up. Okay, so now I'm going to use the right hand rule to try to find what is the force acting on this current that is going up on the right side. Okay, so the current is going up, the field is into. I know that there is a force here pointing to the right. All right. Okay, now let's go to the bottom. The bottom, I'll call this bottom the green part. So here the current is going to the left. Now we have this whole loop, so the current is going to the left. This current now is opposite to the current that was on the top of that wire by itself. Now, so they are opposite. We know that they will repel each other, so there'll be a force pointing down. I can also find that out just by using the right-hand rule, right? Current to the left, field into the page, so the force is pointing down. Okay, and now let's go to the last piece of this loop, this piece here, where the current is going up. Using again the right-hand rule, what we have is current is going up, field is into the page, so we have a force here to the left. Okay, everywhere along this wire, the force to the left and the force to the right are equal in magnitude, and so they will cancel. They are equal in magnitude because at the same distance from the wire 1, we'll have the same magnetic field. No? So let's pick this direction here that I'm showing with this dashed line. So the force here to the right has the same magnitude as the force here to the left. And any other point, the same thing will happen because we have the same magnitude of the field created by current 1, right? As we get further and further from current 1, the field gets weaker and weaker. So the B1 here is weaker than the B1 here. But we'll have the same, we are at the same distance right and left, so these forces cancel. But this is not going to be true with respect to this force that is pointing up and this one that is pointing down, right? The force that is pointing up is stronger than the force that is pointing down. We know that the F pointing up, the magnitude is stronger, it's bigger than the force pointing down. Why? Because the current on top of the loop is closer to the wire 1 than the current at the bottom of the loop. So the magnetic field at the top, this B1 here, is stronger than the B1 that we have down there. Okay, all right, so what we have to do now is, first thing, the direction, since up is bigger than down, I know that we'll have a force pointing up. So the net force points up, points toward that isolated wire, toward wire 1. All right, and now we want to know what is this magnitude. So this magnitude will be the force pointing up minus that force pointing down. So what is the force pointing up? Is the force along that wire 2, in the length of that wire 2 in that piece, no? So it's the whole length of this wire, which is 0.10 meters. Okay, so this is L2. So this is the number we are going to put here, and the B1, but at this region up, where we are closer to the wire 1. And the force pointing down is again the same current, the same length. Now we are thinking about the length here now. So it's the same length as this piece here. Okay, and now the B1 caused by the wire 1, but is the B1 down there, so this B1 is weaker. So let's put the numbers here. Well, let's fill out what that B1 is. So current L2, you know, is just 2.5. Length 2, you know, is just 0.1. And what is this B1? This B1 will be that constant. So you just get that constant. It will be the current 1 through that isolated wire. And now the distance between this wire 1 and the top of the loop. And what is this distance? This value here, 0.3. So I'm going to put here 0.03, right? 3 centimeters is 0.03 meters. And the other part, the other force, I2, that length, so I2 is always the same, is the current going through that whole loop. The length is still the same, is for the bottom part of the loop. And now what is B1? Well, we put the constant, we put the current 1, because that's the current that creates this magnetic field B1. And now we put the distance between this wire 1 and the bottom of the loop. And what is the distance now? Well, this value here, 0.08 meters. So what we have to put here, 0.08 meters. And this result here will give us the magnitude of this force.